Speaking of, let's have a look at an exam question to finish off. So this time we've got a train traveling at a velocity of 30 meters per second. As it passes a signal box, it accelerates uniformly. We get the speed and the time. It then decelerates uniformly. We get told when it reaches the platform. We're going to draw a velocity time graph to show the motion, and then we're going to find the distance, the total distance traveled by the train. Okay, really worth having a go at these questions, even if you just have a go at drawing the velocity time graph. Yeah, it's really good practice to have a go at drawing VT graphs. I would estimate it's very likely you'll have to draw one in the exam. Probably sort of odds on, I would say, to end up drawing one in the exam, so make sure you're really confident with doing that. So if you've got a moment, have a go at this question now, and we'll go over it in a few seconds. Okay, hopefully you've had a chance to have a quick look at that question, and we'll have a go at drawing the graph now. So we're drawing a velocity time graph. That is not a very straight line, but it'll have to do. So the train is traveling at a velocity of 30 meters per second, so we know it starts at 30 meters per second. We'll put that here. So this is velocity in meters per second. So as it passes the signal box, which we'll draw right at the start, so this is the signal box here, right at the start, it accelerates uniformly for 30 seconds. So we can draw that something like this. And that takes us up to 45 meters per second. And that takes 30 seconds. And it then decelerates uniformly to rest, reaching the platform 30 seconds later. So the platform is reached after a total of 60 seconds. It's because it's another 30 seconds on top, and this is a uniform deceleration, so it should be a straight line. I'm afraid this is about as straight a line as I can do, but hopefully you see what I'm trying to do. And that's basically all there is to the velocity time graph. It's not really too difficult to draw, but it's got an acceleration followed by an immediate deceleration. Now for part B, we want to find the distance traveled by this train. We want to find the distance between the signal box here at 0 seconds and the platform, which it arrives at 60 seconds. Okay, so we need the area under this graph to be able to figure out the distance it traveled. To do that, I'm going to split it up into sections. So I'm going to draw some dotted lines on to show you how I'm splitting it up. So you can see this one on the left is just a triangle. This one's a trapezium. Now you can, if you're happy, just figure out the area of the trapezium from this. If you'd prefer, which I do normally, split it up into a triangle and a rectangle, so you don't have to remember the area for a trapezium. I'm going to number these areas. I'm going to figure out each of the areas in turn, add them together, and that should give me the total distance traveled by this train in that 60-second period. So for area 1, we've got a rectangle. So it's going to be the base, which is 30 seconds, times the height, which is 30 meters per second. That's 900 meters. For the second area, it's a triangle, so it's going to be half times the base, which is 30, times the height, which is, the height is from 45 to 30, right? So the height here is actually only 15, yeah? It's 45 minus 30 to get the height. And that gives us 225 meters. And for the final area, number 3, we've got a triangle again. So it's going to be half times the base, which is 30 seconds, yeah, from 30 seconds to 60 seconds, times the height, which is 45 meters per second. So we can figure out that area, which is 675 meters. And all I do to find the total area, the total distance traveled, which I'll call S for displacement. I know it seems strange to use S for displacement. It's just convention, really. It's not because it stands for anything. It's just convention. You'll see it used quite a lot in the next chapters on constant acceleration. So we just add all these areas together to give the total distance. So we do 900 plus 225 plus 675, which gives us 1,800 meters traveled. Okay, and that gives you the answer to part B. So hopefully that made sense. So we've just drawn a velocity time graph. Not too complicated. Just make sure you mark on as much information as you can work out from the question. And then we've just found the distance travelled by considering the area under the graph and splitting that area into simple shapes, so we can easily work out the area of each of those shapes, add them together, and that gives us the total distance travelled by the train. And that's it for this lesson. Next time we'll move on to constant acceleration, which is a really interesting topic. If an object's moving with constant acceleration, we can figure out what distance it travels, what velocity it gets to. And there's also lots of applications for gravity as well, since gravity gives a constant acceleration on an object as long as air resistance is fairly negligible. So there's lots of applications there for projectiles, like throwing things and figuring out how long they'll be in the air for. So we'll do lots of those types of questions next time. For the graphs, have a look at the website at Solve4x. There's loads more graphs there to interpret, and also they give you lots to draw as well. Lots of practice exam questions, lots of quiz questions, and a kind of summary of what we've done in this lesson. So have a look over there if you need more help on the graphs. Hopefully I'll see you next time for the constant acceleration video. Thanks for watching.